Thanks for coming to my session. I'm Chris Weissopel, CTO and co-founder of Veracode. And today I'm going to be talking about application security and bringing a lot of data to bear to get an understanding of the state of what's going on there with software developers all over the world. So the data set that I have comes from Veracode Service. We've scanned almost 10,000 applications over the last 18 months. And the data comes from our static analysis of the software that our customers send to us to test. And the definition of an application is pretty vague. I've seen a lot of arguments about web applications. What's a web application? Because it's certainly not a website. There could be lots of applications running behind a domain. It's easier when it's a piece of software you install, but in general, it varies hugely. So we've looked at applications as small as 100K, like small little mobile apps or small little web apps, to apps that have been 6 gigabytes in size. So you can imagine something that has that much code definitely has at least one vulnerability in it when it's that big. The software we looked at was software that was both in production and software that was in pre-production. It was tested before release. Sometimes that happens, and hopefully it happens. And lots of different sources of software. So internally developed software for enterprises building their own software, open source that our customers want to use and want to understand vulnerabilities in it, vendor code that they're purchasing, and they're looking at the vulnerabilities in that code before they actually pay the vendor for it. And finally, we've been doing a little bit of looking at outsourced code, but it's a pretty small sample size. So in a few places I talk about outsourced code, but in general, outsourcers, their contracts prohibit their customers from actually doing any kind of security acceptance testing because these contracts were written 5 to 10 years ago. And so I think that's going to change in the future, but right now, a lot of open source code just has to be accepted by the customer, and if the customer finds vulnerabilities, then they say, oh, well, you need to pay us to fix them, right? Because it's a rework cost. So have a little bit of data on that. So this is the type of data that we collect. So over here we have the application metadata. So we have some information about the application, what industry is it for, who supplied the software, who built it, what we have some data on the type of application, especially for commercial vendor code, because we can just by the name of the application and the company, we can look up what the software does. That's not always so easy to do on internally developed code. And of course, we know things like language and platform. And we have our customers specify an assurance level. So based on their own risk scoring, do they see this as a critical or high risk app, or do they see it as a medium or low risk app? And then of course we have scan data. That's the data that we generate when we scan it. So it's when was it scanned, what was the date, how many times it's been scanned, and what are the findings. And then we have metrics, which is really what I'm going to talk about, which is counts, percentages, time between scans, days to remediation, and then does it comply with some industry standards out there like OWASP Top 10 or the SAN CWE 25. If you put a policy on it and said, the app has to have no OWASP Top 10 vulnerabilities in it, did the app comply or not? So this is the data set. You can see most of the code we look at is internally developed code. So this is enterprises sending us the code that they're building, and then they're going to operate to make sure their developers did a good job. But pretty significant is commercial code. So this is code that's being purchased by an enterprise, and during the purchasing process, they're going to have us test it. And then there's also some open source. And then, as I said before, the outsource is a pretty small slice. And then this gives you a good idea of what languages enterprises are running, what kind of software they're running, what kind of languages was it written in. And you can see Java is by far the most popular, followed by .NET, C, C++, PHP, Cold Fusion. Surprisingly, there's a lot of Cold Fusion development still out there. 2% is about 200 applications, so that's a significant number of applications. And then some of these platforms are pretty new to us, Android and iOS. We just introduced last year, so we don't have a lot of data on Android and iOS apps. So we have even less on iOS. So I have a little bit of data on Android apps that I'll show you. So a lot of organizations do incident response. They do managed security services. So they have data about the attacks that are happening. If you look at the Verizon data breach report, TrustWave has a report now, and they talk about when they do incident response, what was the attack vector? What was attacked? How did they attack? So what we're doing here is we're talking about the latent vulnerabilities that are out there in the software. So it's a very different view of the software landscape. It's not what's getting exploited, it's what could be exploited. So I did a comparison here of the top 5 most attacked web vulnerabilities. And I found that the web hacking incident database from the Web Application Security Consortium actually had the best data that actually broke it down. A lot of the other reports just say, oh, it was a hack, right? It wasn't a known vulnerability, it was a hack. So they categorize that as someone found a SQL injection or something. But they don't break it down from there, so it's not very useful. So I would, it'd be great if Verizon or TrustWave could break it down, because then we could understand better what types of what classes of vulnerability are being attacked at the software layer. But Web Hacking Incident Database had the best data out there. And so the top 5 attacks for web apps, by far number 1 was SQL injection, here at 20%. So in orange is the percentage of web applications that are affected by that we saw. So in our set of 10,000 applications, 20% here I'm sorry, 32% in the orange here had one or more SQL injection vulnerabilities in them. And from the Web Hacking Incident Database, we see here that 20% of attacks on websites are SQL injections. So you can see that it's obviously a popular attack, and it's in a lot of applications, so that that makes sense. But then you go and look at something like cross-site scripting, and we find cross-site scripting in 68% of the applications that we look at, but only 10% of the web attacks are cross-site scripting's involved. So I think what you can kind of gather from that is, even though there's a lot of cross-site scripting vulnerabilities out there, they're not that useful to attackers. They're not as impactful as, say, SQL injection. So it's just not. It's a vulnerability that's sort of under attacked. There's lots of it out there. So if you put your black hat on, you could say, developers aren't so concerned about cross-site scripting. Maybe I should figure out ways to better leverage and get better impact out of a cross-site scripting vulnerability. If you look at the next category was information leakage. We found that in 66% of apps, and that's really, that's only involved in 3% of hacks. So again, that's something that is very common, but I guess attackers don't find it that valuable to attack with information leakage. Cryptographic issues is another one we find a lot of, 53%, yet only 2% of attacks involve cryptographic issues. Now I look at that, and if I put my black hat on, I think, well, that's probably because people don't know how to exploit these issues very well. And if there were better techniques developed around finding and exploiting cryptographic issues, it would probably be a bigger problem. So cryptographic issues is kind of a bundle of things like SSL not being implemented properly, like not doing certificate checks, allowing falling back to weaker ciphers, things like poor random number generation for security critical values, things like that. And then finally, command injection, we only found 9% of the time, but it was actually used in 1% of the attacks. So again, this is something that is showing that it's probably a pretty impactful attack, because a pretty high ratio of the sort of the latent ones out there are being used in attacks versus what we're seeing with information leakage in crypto is really only a tiny bit is being used. So now I'm going to dive into our numbers. So this here is for web applications, the top vulnerability categories. So these are the types of issues that we find. So this cross-site scripting we find in 68% of the applications we look at. Information leakage 54, control line feed injection 53, cryptographic issues 49, SQL injection 32. So again, there's that number again, very highly attacked vulnerability coming in at 32%. The other thing I've done here is I've colored them orange if they are in the OWASP top 10. So the OWASP top 10 wasn't really built with any empirical data. It was built anecdotally with a bunch of security practitioners talking about what they saw a lot of in applications and what they saw as classes of vulnerability that would be impactful if attacked. But you can see they did actually a pretty good job, because now we have real data from several thousand applications, and you can see that while we have a few things we find, time and state, API abuse, encapsulation, race conditions, that aren't in the OWASP top 10, most of the OWASP top 10 actually does line up with the most prevalent vulnerabilities out there. This is a different view of the data, looking at the counts of vulnerabilities. So the last chart was one or more of a vulnerability in an application counted. And this is actually the raw counts of vulnerabilities. So you can see that 57% of the vulnerabilities we find are cross-site scripting. So it dwarfs everything else because it's so prevalent. And if an application was written by developers who didn't understand how to prevent cross-site scripting, they actually can end up with hundreds and hundreds of these issues. Next was control line feed injection, information leakage, and then SQL injection was 4% of the vulnerabilities found. But a lot of these numbers are really low just because this is percentage based, and cross-site scripting is kind of dwarfing everything else just from a raw prevalence perspective. Now on to non-web applications. So for non-web applications, we used the CWE SANS Top 25. So this is a list put out by MITRE's CWE project and SANS of a bunch of people got together. I was actually on this sort of judging committee where we decided which were the most impactful and prevalent vulnerabilities. And so what were those top 25 issues? And you can see that, again, it's colored in green if they're in the top 25. This one's probably not as lined up as nicely as the OWASP top 10, but you can see cryptographic issues are very prevalent in non-web applications. One thing that really surprised me was directory traversal, how prevalent that is. Because we see that that's not really exploited that often, and that could allow an attacker to read or write potentially any file on the system. If it's typically when a file name is created with user-generated input. And so, my theory here is that people just aren't looking for directory traversal because they don't think they're that valuable, or they don't think they're going to find them. But I think that's an area that if I was putting my black hat on, I would start looking for directory traversal issues. Again, you see down here in non-web applications, we have some classes of issue like buffer management errors, buffer overflows, and numeric errors down here, which we typically don't see in web applications because web applications are usually written in scripting languages or type-safe languages like Java and .NET, which don't have those problems. So we're seeing additional types of vulnerabilities show up here in non-web applications because of languages like C and C++, which these things are pretty prevalent in. But again, we're only seeing buffer overflows in 14% of the applications we look at. Buffer management errors, another memory corruption issue, class of vulnerability in 17% of applications. But then when we slice the data and look at the overall prevalence of these categories, we see buffer management errors and buffer overflows are towards the top at 15 and 14%. And that's because of an application, if the application was developed with no concept of correct buffer handling, again, it's like cross-site scripting. It just becomes a pervasive problem if the developers weren't using proper bounds checking around their buffer management. And so that's why, even though they're in a low percentage of applications, they end up being towards the top in overall prevalence. And error handling is still the biggest issue, but that's not really that exploitable. The other thing that's interesting is we see a lot of potential backdoors, and that isn't in the SANS CWE top 25. And that's sort of a bundle of different things where there could be some, it looks like there's some potential, malicious code in there. Either it could be intentionally put in or it could be non-intentionally. And that's things like hard-coded passwords and keys and hard-coded IP addresses, debugging functionality. Good example of this is, and it's not necessarily malicious. Sometimes companies put this in their product for customer support reasons, or the developers had it in there for debugging, and they left that in the shipping product. So it's not always malicious, and we actually find that more than you would expect. It's at 9% of the issues we find. So next I want to take a look at by language, because the language you program in makes a big difference in the kind of vulnerabilities the application is going to have. And it's both sort of at the raw language level, and that's in the types of APIs, whether it's runtime or a framework that's used to program in that language that either supports writing secure code or doesn't support writing secure code. And it also is how the developers are trained to write in these different languages can either support or not support secure programming. And so if we look at Java, we have cross-site scripting, control line feed injection, and information leakage. So it seems fairly safe because the top categories aren't all that exploitable or they're being exploited. But then if we look at cold fusion, its second biggest category is SQL injection at 8%. So cold fusion doesn't really support a coding style, or the developers aren't trained in such a way that they're able to prevent cold SQL injection the way that Java developers are. So what this tells me is if I run into a cold fusion application, I'm much more likely to find SQL injection than if I run into a Java application. Now, there's more Java applications out there, though. But still, it shows that the language really does make a difference here. And if we look down here at C and C++, we can see that buffer overflow and buffer management errors are number 2 and number 3. So if you have that type of compiled C and C++, we all know that those are really endemic problems with programs written in those languages. .NET looks a lot like Java was with cross-site scripting, information leakage, but cryptographic issue shows up where it wasn't on Java. You see up here, number 3 is information leakage. So it tells me that .NET isn't supporting writing cryptography as well, or the developers aren't trained as well in cryptography. PHP, again, it's sort of like Cold Fusion. It's not supporting writing code that doesn't have SQL injection in it as well as .NET and Java are. So again, if you have a PHP application, more likely to have SQL injection, and you can see here that directory traversal shows up. And directory traversal isn't in the top 3 of the other languages, and we got directory traversal showing up in PHP. So PHP, just from a web standpoint, looks pretty bad, right? It looks like we got some two serious categories here. In addition to cross-site scripting, which seems to be everywhere, we have SQL injection and directory traversal. So if anyone's done auditing of PHP apps, they know that these issues are more likely with PHP apps. And then I threw in Android, even though we have a sample only of 100 Android apps to show what are we finding in Android. And it actually ends up being a lot of cryptographic issues, which is pretty interesting. So it looks like Android developers don't understand how to use the crypto APIs well on the platform. And they're also baking in a lot of static crypto keys, which is definitely a bad idea. A lot of data here. And so this is looking at the vulnerability distribution by the supplier type of the application. So supplier type is who developed it. So was it internally developed? Was it commercial code? Was it open source? Was it outsourced? And if you look across something like cross-site scripting, you see, and take the outsourced stuff with a little grain of salt here because it's a small sample size. You see this is pretty consistent. Everyone's writing cross-site scripting errors. That's really consistent. SQL injection ends up actually being consistent too. We got 4% here, 3% here, 3% here. So based on supplier type, it looks like those are very consistent. But if you look at directory traversal, it goes from 3% internally developed to 6% commercial to 13% open source. So there's definitely a difference with directory traversal. I have no idea why that might be. I haven't been able to figure that one out. So if anyone has any ideas why that would change, and it looks like a significant numbers. I don't know why that might be. But this one's another thing that's different is commercial code. We're seeing buffer management errors and buffer overflow. And I know why that, and it's not in any of the other categories. And that's because they write their code in C and C++. Yeah, any question? What's that? This might be a lot of PHP, right? There's a lot of open source PHP web apps. That might be true, and we saw before that PHP was the problem for directory traversal. So maybe, internally developed never uses PHP, commercial uses a little bit, and open source uses it a lot. I mean, that perhaps one explanation. And then we slice the data by industry. So this is, who's going to be operating the code, whether they built it themselves or they're purchasing it, who's operating the code. And this government is all U.S. government. We don't have any foreign government customers. For some reason, they don't want to send the code to the U.S. because of the U.S. Patriot Act, I think. But the government doesn't mind because they already have the code. And then finance and software were two other industry verticals that we had a significant amount of data in. We do have data from retail, manufacturing, healthcare, but the sample size for those was less than 100 apps, so I didn't want to use that data. But for these, we have thousands of apps in each of these categories. And you can see that there's a significant difference with cross-site scripting. Government, 75% of apps were affected. Finance 67, and the software industry 55. I think the software industry is probably because they're writing a lot of non-web apps is probably part of the reason. But it's interesting that finance sort of is doing a little better job, writing their code to not have cross-site scripting. But this one really stood out for me. SQL injection goes from 40 to 29 and 30. So the government's writing code with a lot more SQL injection issues in it. So they should definitely change something there. That looks like a pretty high number. So if you're going to attack government websites, I probably didn't have to tell you this, but you'll find SQL injection there. So then we looked at trends over time. Is any of these vulnerability distributions percentages changing over time? Because it would be nice to think that with more technology available for testing, more training available for developers, and we've known about these issues for a long time, that we might actually be writing better code over time, right? You think it could happen, right? Well, so we looked back, I think it's 8 quarters, so we looked back 2 years on cross-site scripting. So we looked at our database, we looked at our data for 2 years, and we found that cross-site scripting is essentially flat. It looks like the trend's a little up, but the p-value has to be below 0.05 for it to be statistically significant. So statistically, it's a flat line. So in 2 years, the code that we've seen at Veracode has not improved at all with cross-site scripting. It's almost exactly the same. But for SQL injection, the word is getting out. Somehow, after dozens of break-ins every year, high-profile break-ins with SQL injection being the cause, it's starting to make a difference. And the trend is down over 2 years, and it's about 38% here applications were affected 2 years ago, and today we're seeing about 32% of our applications being affected. So over a 2-year period, it's decreased 6%, which it seems slow, but it's pretty good news, right? Actually, there's some good news in my report that it's getting slightly better. I guess the bad news is unless that accelerates, until it gets into single digits, it's going to take 6 or 7 more years based on that trend. So maybe we're seeing the lifetime of a vulnerability here, discovered in 1998, and by 2018, perhaps it'll be eradicated. So that could make a fun white paper someday. And then we said, well, let's do a deep dive on one sector, and we picked on the government this time because that looks like fun. And we said, how are they doing? That was all industries, all code, and how's the government doing? So again, with cross-site scripting, it's flat. You can see this gray line here is the line from before for all industries, and the orange line is just for the government, and statistically it's flat. And then if we look at SQL injection, it's flat again. So it looks like it's going up instead of down. Like this is the one before, the gray line going down. It looks like it's going up, but statistically it's flat. But while everyone but government seems to be doing a good job at lowering SQL injection, our government customers don't seem to be able to do that. So I think part of the explanation for that is there's not enough training, for one thing. And if you look at the US government standards, there's a standard from NIST called 800-53, which is a security control standard that all government agencies in the United States have to abide by. There's a law called FISMA, the Federal Information Security Management Act, I think it is. And they have to, whatever's in the controls in 800-53, every agency in the government, in the US government, is graded on this. And there's nothing in there that specifies application security. Web apps aren't mentioned, SQL injection's not mentioned. It's things like you must have encryption, right? So if there's no compliance reason, and there's no risk-based reason, and there's no cost reason to write secure code, you're not going to. So it just doesn't happen magically. That's why we have to have some standards in the US government at least to improve the situation. And so there's a new version of 800-53 coming out later this year, which specifically mentions doing things like static and dynamic analysis while you're building applications and for apps that you purchase. So I think this is going to change, and it'll be interesting to see over the next 2 years if my hypothesis is right and the trend for the government, US government, starts to go down. So now it's the quiz time. What percentage of web applications do you think fail the OWASP top 10? So they can't have any issues that are listed in the OWASP top 10. How many people think it's A? Nobody. How many people think it's B? We got one person? 2 people? How many people think it's C. Okay, I got a lot of people. And how many people think it's D? Oh, we got a lot of people there too. A little more on C, and the answer was C. That overall 86% failed. Open source actually came out the worst, and my theory there is open source web applications really aren't written that well, and they typically don't do anything with financial data or credit card data, so they probably aren't held to any kind of compliance standard, where if you look at commercial and internally developed code, they're doing the best, even though it's really poor, because there are a percentage of applications that are held to a standard like PCI compliance, or perhaps they were just well written. And then if we look at the OWASP top 25, so this is we didn't find any issues at all in the whole OWASP top 25, which you'd think is a stricter standard because there's 25 things to look for in there. Generally, software did better. And I think it's just because of things like cross-site scripting is so prevalent in web applications. It's rare that you don't find any. And it turned out that internally developed code actually did the best, followed by commercial and open source code. So then we looked at what industries are securing their supply chain. What industries are holding their vendors accountable, because this is kind of a new concept. Like, people started securing their own code, because if they didn't secure their own code, who was going to do it for them, right? If you're writing the code, you have to. But if you're purchasing code, there's this kind of assumption that the vendor's doing the right thing, right? The vendor, they're a commercial software vendor. Of course they're writing secure code. I think that's kind of the mentality, but people are starting to do security testing as part of their acceptance process when they purchase code. And so these are the different industries that are using Veracode to do this. So by far the biggest is the software industry and the IT services industry. It's interesting to think about, but software companies actually buy a lot of software, both to run their operations and to include in this. They bundle software they purchase from other companies in their packages that they sell. So they're the biggest user of third-party risk management. And the second is the financial services industry, kind of on the leading edge of anything to do with application security. And then we're starting to see some emerging industries start to care. We're starting to see aerospace and oil and gas industries start to care about the code that they're purchasing. And then we've seen a little bit from these industries, but it's less than 1%. And it's interesting to see that the government doesn't really care about the code that they're purchasing. And then we looked at what types of applications do people want to measure the security of, right? So it turned out that the number one was operations software, so like IT operations software. Second was financial software. And then security products was third, which I thought was pretty interesting, that people are looking at the security of the security products, the secure coding of the security products they're purchasing. And then we had learning and growth and customer support. So that's the data set that these next numbers come from. So then we looked at, we allowed the companies to set an enterprise policy. So we didn't use OWASP top 10 here or SANS CWE top 25. The companies set a policy, and it could have been a policy like that, but it was whatever their policy was, whatever they deemed was acceptable. They chose the policy, and this data is based on what they chose. And it turns out that the worst code comes from security products. 74% of security products failed. And if you look at financial products, only 37% failed. That's a huge difference. It's like twice as much. So, software vendors that write financial packages are doing a good job writing secure code, and security product vendors are doing a bad job of writing secure code. It doesn't surprise me. I used to work at a security company. But I think it's a good wake-up call to the marketplace to, and people have written about this before, that as you layer on security products onto your hosts, onto your servers, onto your networks, you're actually layering on vulnerabilities along with layering on controls. Next worst was operations software, which again is things that are like, you know, doing things like running your IT infrastructure. Again, not so good. But overall, it was 60% failed. Yep.
Question. Do you have any information how many of these customers are requesting that vendors are responsible for fixing vulnerabilities and something about their processes? Because that's something at the time.
Right. So sometimes this testing is done during the acquisition process where they're testing two products, and they use the secure coding as one of the criteria, along with price, performance, features. They'll also use that as a criteria. So sometimes, if a product is really, really insecure, they just won't purchase it, and they're done with it. But if they purchase the product and it was insecure, what they'll do is in the contract, they'll say, within a certain period of time, you need to remediate the high and critical vulnerabilities. So they basically say, okay, we'll take it now, but we expect in your next point release, maybe in 3 months, maybe in 6 months, that you're going to fix those problems. So it's both can be used to reject something, but it can also be used to put a strong remediation plan in place with the vendor. And that seems to work if it's during a purchasing cycle, because the salesperson and the company wants to make the sale, and if it's a big dollar amount, they're willing to actually fix their code. This is another thing we took a slice on software vendors. And we wanted to see if there was any difference among the type of software vendor. Was it a public company or a private company? What were their revenues? Did big software companies write better code than small, little, tiny software companies? Because, you know, we've tested code from software companies that had like five people. And it turns out that public versus private doesn't make much difference. This is a whisker chart where the middle is the median, and this is the sort of the standard, two standard deviations. Turned out that they were very comparable, public versus private. And then also by revenues from 50 million to 50 to 500 to 500 to $1 billion and $1 billion and more are pretty much the same, which actually was pretty surprising to me, because you hear from a lot of big software companies, Oracle being one of them, saying, you know, we have a great security program. We're a big company. Big companies don't need to have their code checked. We've got it covered. And this data shows that that's wrong, that small companies, medium-sized companies, large companies, it doesn't matter. They all write about the same quality code. So I have a little bit of data here on smartphones. Like I said, we don't have a lot of data because we just introduced Android and iOS static analysis middle of last year, and we took the data through the end of the year to do our report on. And so we have some data on the industry verticals. I should say that when we do like Android applications, these are enterprise Android applications. We're not going up to the marketplace and pulling down hundreds of apps and just looking through them. It's something we could do, but we haven't done that. And if we did that, then we'd get the distribution of what's in the marketplace, which would be heavily slanted towards things like games and personal productivity apps and things like that. But these, the apps that we've tested are apps that our enterprise customers are either building to give to their customers and partners or employees, or they're buying. So they're serving an enterprise purpose. And so the breakdown is, you know, mostly retail, then technology, companies, finance and services, banks, media, healthcare, hospitality. So these are all the different companies that are either buying or building enterprise mobile apps. And when we looked at them, the number one vulnerability was insufficient entropy, which basically just means that no one's using secure random number generation on Android. They just don't get the concept or something like that. This one was really surprising, though, is hard-coded cryptographic key, because that means if you have possession of the binary, you're going to have possession of the key, which I can see how an enterprise developer might think like, well, it's connecting to our back-end service and we're only giving these applications to our employees, so everything's cool, right? I can hard code the cryptographic key. But if the phone gets lost and that app gets taken off the phone, then you're going to lose the key. So that's always a bad idea. I mean, to hard code it, because then you can't change the key easily, and there's a huge amount of people that know the same key. And we see this in regular Java applications. I think it's about 18% of the time we see it on a Java J2EE application. But it's much worse on the Android, and it's also much worse because of the threat model, right? Like, you'd have to break into the application server and be able to read the binary to get a hard-coded key in a web application. But for on an Android device, you just have to get access to the mobile app, which is widely distributed. And then some of the other categories is information exposure through sent data. We saw 39%. So because of the sort of the threat model of the mobile device, where there's a lot of the big threats are not someone compromising the device through a buffer overflow or SQL injection and things like that, where they would take over the device to get the data. A lot of times that the risk is the app is written insecurely and is leaking data. So it's leaking sensitive information in the clear, or it's using sensitive information like the phone number and things like that as IDs and tokens in the way the app is built. So this is all about data that the user of the device doesn't want sent off the device, and it gets sent off. And so this is a big emerging area in the mobile world. And it isn't always that the app is written insecurely. Sometimes the developer wrote it on purpose to have sensitive data go off the device, right? Because that was their business model. Like we saw this big thing with, I think it was Path, with the address book. And so Veracode, we wrote a small app that just did a quick binary grep to see how many apps that you had installed happened to be for iOS, because it was easy to look in your iTunes directory, and see how many apps you had installed that access the address book. There's a method which bulk grabs the whole address book at once, and it turned out that we found hundreds of apps that are doing this. So sometimes it's intentional that's going on. Of course, an enterprise purchasing a mobile app doesn't want their employees' address books all compromised by the mobile app provider. So that's why they would be concerned. But individuals should be concerned too. So now I want to talk a little bit more about developers and how well developers are doing about writing secure apps from an education standpoint. So when given an exam on security fundamentals, over half developers, how many people think they received an A on the assessment test? Nobody. How many people think they received B or worse? Again, nobody. Received a C or worse. So we got about a third of the room. And how many people think they got a D or an F? About the same. So it actually turns out to be C. About half get a C or worse here with the overall score. I'm sorry, that was the application security fundamentals. So that's this data up here. But you can see the breakdown of scores A, B, C, D, and F for these different assessment tests. And these are the top 4 assessment tests that we give out. And so this is a set of about 5,000 developers that this data comes from. And so down here is the types of tests that organizations are asking their developers to take. So 62% take the application security fundamentals, which is really basic stuff that applies to every language, like theories of least privilege, input validation, those very basic concepts that apply across all languages and platforms. And then we have tests like secure coding for .NET, which is .NET specific issues with the .NET APIs for Java, and intro to cryptography. And it's interesting that developers actually do pretty well on cryptography. And if you ask a developer if they learned security in school, they say, yeah, I learned security in school. I took a course on cryptography. So cryptography is actually taught at the collegiate level. And so a lot of developers know about, more than half of developers got an A or a B. Actually, almost half got an A on crypto concepts, which again, I think shows that if you educate the developers, they'll actually know what they're doing. But if you look at security fundamentals, which you think are the really basic things that we all know about building secure systems, developers actually fare the worst. They don't really understand concepts like least privilege and attack surface reduction and things like that. And then another difference here was interesting that the secure coding for .NET did a little bit better than secure coding for Java. My theory, because A and B's comes to 66 versus 52 here, so that seems significant to me. And my theory there is, and I've looked at the .NET documentation, it talks a lot about using the security features, things like output encoding and input validation, and it's right there in the .NET documentation. So I think just by learning how to code in .NET, the developers absorb some secure coding concepts where that's just not happening with the Java developers. So then we took a look at, can we correlate the test scores that the developers on a particular development team got with the security quality score that we generated for that application. And it turns out that it doesn't really correlate very well. So we were hoping to see that the people that did well on the tests, so they knew about secure coding, actually wrote more secure apps. And which would show a nice trend line here, right? But it looks like it's spread all over the place. So I think we need to do a better job of isolating our data better. I mean, one of the problems is a developer could take a test and then join a development team that's written bad code for 10 years, and he's on that team now, and he might be writing good code, but there's such a security debt of bad code, and it's hard to isolate that. So what we really need to do is look at pieces of code that were written by a particular developer, and we can't just conflate teams and applications together. So that's something that I'd like to work on to actually show the value of education, because intuitively it makes sense, right? But I don't think anyone has empirically shown that it makes a significant difference. Is there a question back there? Right. No, that's true. You're right. This could be correct. This could be correct. There could be no correlation. Even though a lot of companies are spending money to train all their developers, hoping that there will be an effect, right? And it's something that I see a lot of people starting when they say, I'm doing an AppSec program. The first thing we're going to do is we're going to train our developers, right? I find that's probably like half the time I hear that. And I say, well, really what you should be doing is testing, because then you're putting in a verification, you're putting in an enforcement mechanism that's going to force you to remediate things. But then you need a policy and hold your developers accountable to do something. And that's harder to do than offer training. So that, besides this interesting math problem here, that was all I had for for data. So if there's any other questions, I'd be happy to take them. Who's going to be first? No questions? Okay, well, thank you very much for coming.